Hey everyone, thanks for joining us today. We're excited to have you here for a webinar on MetaGeek's IPA packet analysis software. Our presenters today are Aham Susi from Arachnus Networks and Joel Crane from MetaGeek. My name is Heidi Nilsson and I'll be the moderator today. Before we get started, let's go through a few quick housekeeping items. First, we will have a recording of today's session available for you afterwards. Within about 2 business days, we'll send you a follow-up email with a link to the recording, and we'll also have a coupon code for you for $50 off the MetaGeek Basic, Pro, or Advanced packages, so be sure to look out for that email. And lastly, we are planning to have a Q&A session at the end of the presentation. You can send in your questions at any time throughout the presentation using the question and answer feature. We'll answer those as they come in and we'll save some for the end. And with that, I will turn it over to Joel.
Awesome. Thanks, Heidi. Thanks for joining us for this webinar today, everybody. So just kind of a quick introduction so that you know who's talking on the other end of the microphone here. My name's Joel, and I'm the trainer at MetaGeek. I do things like write knowledge base articles and teach webinars like this, make videos, things like that. So pretty typically when you find some kind of training materials through our website or various sources like that, typically it's going to be something by me. So I really enjoy this job. It's a lot of fun. I really enjoy Wi-Fi, and I think that we're going to have a great webinar today. So let's go ahead and jump right in. Now just kind of so what you know what to expect throughout the course of this webinar. If you attended our last webinar, the spectrum analysis webinar, there's going to be some similarities here. I'm going to build on some of those things that we learned in that last webinar. So if you haven't had a chance to check that out, be sure to visit SnapAV and get a copy of that and watch that, because we're going to build on some of those concepts that we learned in the spectrum analysis webinar. And of course, we'll quickly touch on spectrum analysis and talk about how that ties in with packet analysis. But to really understand packet analysis, to really get it, there's some really important things for you to understand. There's some concepts that we learned about when we looked at spectrum analysis that we're going to build on as we look at packet analysis. So the first thing that we need to talk about, we talked about this in the spectrum analysis webinar, is how Wi-Fi is half duplex. And I'm sure you remember that we talked about how Ethernet is full duplex. And that means with an Ethernet cable, we've got multiple twisted pairs of copper inside the cable, and that allows us to send traffic in 2 directions at the same time on the same Ethernet cable. But if you remember, Wi-Fi is half duplex, which means only one side can talk at a time. It's kind of like this. If an access point needs to transmit some data, and if it transmits the data at the exact same time as maybe a laptop or another client device, that data is going to collide, and those two devices are basically going to cancel each other out. It's just like a human conversation. If you talk and if I talk at the exact same time, we're going to simply cancel each other out. So Wi-Fi is half duplex. We can only send traffic in one direction at a time. Now, we talked about this in the packet analysis, or rather the spectrum analysis webinar as well. We talked about this constant process of how we send data from one machine to another and we reply with an ACK or an acknowledgement. And again, we're going to get really in-depth with this in this webinar today. We're going to talk about those processes a lot. But one thing that I want you to remember, one thing to recall, is that when we send data to another machine, remember that data is going to, when it arrives, the receiving device is going to look at that data and make sure that it understood it. And if it did, it'll go, yep, check, I understood that data, and it will reply with an acknowledgement. But remember, there's some things that can go wrong here. If, let's say that the access point transmits that data, but it never makes it there and just gets garbled along the way, there's several things that can cause that. Maybe another device on an adjacent channel started talking and garbled up that information, or maybe the laptop is just too far away. It's just so far away it can't hear the access point very well. You remember what will happen in that case. In that case, the access point is going to transmit that data. The data never arrives, and so the laptop never sends that acknowledgement. And after a while, the access point is going to start going, okay, well, I transmitted that data, but I never heard an acknowledgement. And so it's going to retransmit that data again and again and again. And what's really great about packet analysis is that with packet analysis, we can see exactly how often and exactly when this is happening. With packet analysis, we get a lot closer look at what's going on. Now, you also remember in the half-duplex nature of Wi-Fi, how on any given channel at any given time, only one device can talk at a time. Let's say, for example, that we have an Android phone here, and that Android phone is currently transmitting some data to this access point. When that data transmission is occurring, all of these other devices have to be quiet and wait for their turn to talk. Only one device can talk on a channel at a time. And the more and more devices you add to a channel, the smaller and smaller and smaller everyone's transmit opportunities get. I like to liken it to a dinner table conversation. If you have 4 people around a dinner table, with 4 people, it's going to be a pretty nice conversation. You're all going to politely take turns talking. Everybody's going to get plenty of time to talk. But when you go to the in-laws' house for Thanksgiving dinner or something like that, maybe there's a ton of people around the dinner table. Maybe there's 15 or 20 or 25 or maybe even 30 people all crammed around a dinner table. When you get that many people around a dinner table and you're all having one big conversation, it gets really, really difficult to get a word in. The exact same is true with Wi-Fi. The more devices you add to a channel, the smaller and smaller everyone's transmit opportunities get. And we also have to think about speed as well. How does speed factor into this? Well, when we think about speed, wireless devices are constantly switching their data rate. That is how fast they can talk. At any given time, a device is going to be switching anywhere from 1 megabit per second, maybe 24, maybe it'll go all the way up to 54 megabits, or maybe 270 megabits per second if it's a good 802.11n connection. And then if there's some background noise, it might start falling back down to a slower data rate. The distance from the access point matters as well. If we've got a device that's kind of far away from an access point, as a device starts to move away from that access point, it's going to fall back to a slower and more reliable data rate. Wi-Fi data rates are constantly changing, and Wi-Fi data rates directly affect the half-duplex nature of Wi-Fi. In fact, this is probably one of the most critical aspects of Wi-Fi when it comes to data rates. So let's look at this example for a second. Let's say that we have an Android phone here, and it's relatively close to the access point. The environment's fairly quiet, and so it's able to maintain a nice fast data rate, maybe 54 megabits per second. Now remember, this is the physical rate. This is the phi rate. This isn't the actual throughput that we're going to get. We're only going to get about 60% of that. We're only going to get about 60% of that due to management overhead. But let's say that we're getting a physical rate of 54 megabits per second. Meanwhile, on the very fringe of the coverage area, we've got another Android phone that's very, very far away from the access point. And since it's so far away from the access point, it's had to fall back to a slower data rate. It's had to fall all the way back to 1 megabit per second. When that happens, this slower device, this device that has fallen back to that slower data rate, will take 54 times longer to transmit the same amount of data as a device that's close to the access point. It will talk slower. It'll get on the channel and slowly transmit all of its data, which consumes time. I like to think of a device that's using a slow data rate as the slow kid in the back of the classroom. You guys know who I'm talking about? Have you ever encountered the slow kid in the back of the classroom? They're that guy where, you know, the class is going along nicely, and this guy in the back of the classroom raises a hand and goes, teach, I had a question, and you're just like, dude, spit it out. We're paying $50 an hour, $100 an hour, or whatever to be here. Say what you want to say. It's the exact same way with Wi-Fi. Slow Wi-Fi devices that are using slow data rates are like the slow kid in the back of the classroom. They raise their hand and they talk slowly and they take forever to ask just that stupid question, and you just wish that they would shut up so that you could move on with a class. You guys know who I'm talking about, don't you? We've all encountered that person before. So that's exactly what it's like with Wi-Fi. We want devices to get on the air and get off the air really, really quickly. We want them to get on and get off quickly, transmit their data, and then be done so that we can free up time for other devices on the channel to talk. And so we have to think about that. This is essentially what happens with co-channel interference. You remember this. You remember how we reviewed these 3 different types of interference. Adjacent channel interference occurs when we're on partially overlapping channels, and networks and all their connected devices just yell and scream over each other. Co-channel interference is the better type of interference, but it's still something that we have to think about. It's still something that we have to contend with. Every client and every access point on the same channel is going to compete for time to talk, and so we need to make sure that devices are getting on the air and getting off the air quickly. The other thing to consider here is retransmissions. Remember when we talked about that? We talked about how if a signal gets garbled along the way, we have to retransmit our data. Now in Wi-Fi, that actually happens fairly often. In a normal, healthy environment, it's not unusual to see devices retransmitting 8, 10, maybe even 20% of the time. But retransmitting frames, repeating yourself, saying the same thing again, like I just did 3 times, takes up time. It takes a lot more time to do that. So not only do we want to keep our data rates nice and quick, we want to make sure that we're not repeating ourselves either. We want to make sure that we're having a nice, fast, and consistent conversation. So So how do we look into this? Well, packet analysis is best for looking at co-channel interference. It's great for looking at a specific channel to see what is happening on that channel. With packet analysis, we're able to capture all of those wireless frames on that channel. We're able to capture all of that and look at those conversations between laptops and tablets and smartphones and access points. Packet analysis shows the details about 802.11, that's Wi-Fi congestion, on a specific channel. Now, one thing to watch out for, you're going to hear me say the word packet a lot. But the funny thing about this is that in Wi-Fi, they're not actually packets. They're actually frames. Packets happen at a layer 3 networking level, right? When you're moving packets of data around on an Ethernet cable and out to the internet and back and forth and things like that. At a Wi-Fi level, they're really more of one more layer down. They're down in layer 2, and they're really called frames. And so keep that in mind. You will hear people use the term packet analysis a lot, but if you really want to be completely correct about it, you would say frame analysis. You're going to see me go back and forth as I talk about packets and frames. Just assume that I'm talking about the same thing no matter which terminology I'm using. So we always want to start with layer 1, with the physical layer. Now let's stop in for a second and think about Ethernet. If we were troubleshooting Ethernet, and let's say we were having some trouble with an Ethernet connection, how would we handle that? Well, with an Ethernet connection, the first thing I'm going to do is I'm going to see if it works, right? I'm going to plug it into a computer and see if we can go to google.com or something like that. And if we can't, if it doesn't seem like there's any kind of network connection there, what's the first thing you're going to do? You're going to test the cable. Now, there's a couple of ways that you can test the cable. You can use a fancy cable testing tool. I'm fortunate enough to have a really nice little cable testing tool where you plug it in and it checks for a link and it tries to get a DHCP address from the network, and then it tries to ping Google. And it's just a great little tool for testing Ethernet. Or a more lower tech but just as effective way of doing it is maybe you'll just try to replace the cable. Either way, you are testing layer 1. That is the physical layer. That is the actual copper inside the cable that is going between your computer and your networking switch or whatever device is on the other end. With Wi-Fi, we want to do the exact same thing. We want to quote-unquote test the cable, and we're going to do that with spectrum analysis. A spectrum analyzer shows us all of the raw radio frequency activity in our environment, and that's going to guide us to the next troubleshooting step. So for example, let's say that we open up a spectrum analyzer, and on that spectrum analyzer, we look at the air, we look at the raw radio frequency activity, and we see a non-Wi-Fi signature. In this case, we might see this device, which we can use Channelizer and the Wi-Spy to identify what kind of device that is, and we can say, oh, hey, look, there's a cordless phone and it's causing interference. And so we need to do something to correct that problem. You're going to use spectrum analysis to identify and remove the non-Wi-Fi interference. The other possible thing that might happen is you might look at in the spectrum and you might see heavy Wi-Fi utilization. This is what Wi-Fi looks like on a spectrum analyzer. So when you fire up your spectrum analyzer and you see that there is a Wi-Fi signature there and it's on the same channel as your wireless network, that's when you go, oh, okay, well, we're not looking at a non-Wi-Fi interference issue. We're looking at heavy utilization on that channel. There's a lot of activity happening on that channel. At that point, you might use layer 2 packet analysis to dig deeper into that Wi-Fi conversation to see what is causing that congestion and why. And that's one of the things that you might do with that. So let's take a look at those scenarios really quick. I just switched over to my Windows virtual machine here, and I'm gonna start up. I've got Channelizer running here, Channelizer and a Wi-Spy, and let's find our network really quick. I'm going to turn on my networks here, and I'm going to come down to the networks table, and I'm just going to apply a filter. We're just going to type in MetaGeek Lab. We're just going to filter down to the network that I care about right now. So there it is. There's MetaGeek Lab. We'll switch to logical mode so we give it a nice friendly name. Oh, where did it go? There it is. So we can see that MetaGeek Lab is hanging out right there. And let's say that we were troubleshooting an issue where this device or this network would just randomly drop out and stop working. If we fired up our spectrum analysis tool and we saw a spike shape like this spike shape right here, and if we saw that shape would sometimes end up on the same channel, on the same frequencies as our wireless networks, then that might be a problem. That would basically block that network from talking. If you remember from our last webinar, these non-Wi-Fi devices, not only do Wi-Fi devices need time to talk, but non-Wi-Fi devices need time to talk as well. They need to be able to get on the air and say what they need to say. Now, some devices talk more than others. Bluetooth devices don't talk very often. They only talk about 10% of the time, so typically they're not going to cause a lot of trouble. Whereas an old analog device like this cordless phone, if you look at the color tells us that this thing is talking constantly. It's like an air horn. It just won't shut up. And so this would basically block any Wi-Fi devices on that channel from talking. Those Wi-Fi devices would back off. Now, fortunately, it's not interfering with MetaGeek Lab right now, but the problem is that this cordless phone has a tendency to switch channels. If we turn it off and turn it back on a few times, this time it looked like it decided to stay on the same channel. It knows that I'm giving a webinar and it's being difficult. But this cordless phone is known for switching to different channels constantly, to constantly moving to all kinds of different channels. There we go. It decided to cooperate and moved over here between channels 3 and 5. And that's going to severely limit how much this wireless network can talk, if at all. So let's say that we need to find this network and we need to get rid of it. If we go to the interference tab, this is that library of common shapes, different things that we might see in the spectrum. And we can go through here and we can kind of make some comparisons to see if it matches up or not. And I'm going to say that looks a lot like this Uniden cordless phone. I'm going to say that's probably what that is. And now that we've identified it, we can actually go track that device down and get rid of it with the device finder functionality. So that's just one of the possible ways that this might go. But let's say that there is no non-Wi-Fi interference. Let's say that we don't see any non-Wi-Fi interference. Instead, we see a ton of Wi-Fi activity on that channel. Now, to simulate this, I'm actually going to do a throughput test. I'm going to do a throughput test with a little command line tool called iPerf. It's I-P-E-R-F. iPerf is a great tool, and I know that sometimes the command line is scary, but this tool is so easy to use. It's extremely easy to use. So on one machine, on one side of your network, preferably plugged into the Ethernet side of your network, you would install iPerf on a machine, and you would just run this little command. You just run iPerf3 TAC S, and that just means server. So now it's the server. And then on the client side, which is where we are now, which is perhaps a wireless device, we can run iPerf TAC C, that means client, and then type in the IP address of the server. In this case, the server is just a little Raspberry Pi. It's one of those $35 computers, and I've just got it plugged into the Ethernet side of the network. And so now I'm going to go ahead and run this throughput test. Now, this is a lot. This is a lot like what you would see with a throughput testing tool like speedtest.net. But the advantage here is that we're just going local on the network. And so that means that we could test at this case, we max out at 100 megabits per second because the Raspberry Pi has a 100 megabit per second Ethernet adapter on board. So let's go ahead and run that command a few times. And what you'll see is that while this command is running, you'll see in the waterfall view, you'll see we'll see this activity show up here. And if you look up here in the density view, you can see that there's kind of this flat tabletop shape forming up here. Now, there is some commands that you can run here to make this run for a very long time. I'm just letting it run for the default window of time, which I think is something like 10 seconds or something like that. But if we keep running this throughput test repeatedly and moving a bunch of data across the air, we see this very uniform kind of flat tabletop shape form here. And if we go to the channels table, we can look to see exactly how often that channel is being used. In this case, we're keeping it utilized about 24%, or I'm sorry, that's channel 1. About 45% of the time. So we're keeping that channel pretty busy right now just by running this throughput test. Now there's all kinds of different things you can do to simulate this. You can move a big file across the network. You can stream a high-definition YouTube video. There's all kinds of things, but iPerf is just a really neat and simple little way of doing this. So let's go ahead and pause our recording. And actually, I'm going to start a new session here. So let's just start a brand new session and run our throughput test a couple more times. I just want to make it a little easier to grab large portions of time. So we'll start our throughput test here. So that's running right now. And then let's just take a look at how often we are utilizing the spectrum in that little window when we run this a few times. So we'll just let it gather, I don't know, maybe 30 seconds worth of data or something like that. Now, one thing I want you to take note of is that we're doing this in the 2.4 gigahertz band right now. And 2.4 gigahertz, if we look at the whole thing, it's pretty nasty. This is a very, very crowded environment. And in fact, my Wi-Fi adapter is plugged into my laptop here, and my access point that I'm testing to, which is just an old WRT54G, by the way, is only about 5 feet away. Yet we're only seeing about 3 to 5 megabits per second, sometimes even 1 megabit per second. It's performing pretty badly. That's how toxic the environment is here at MetaGeek. So if we look, let's take a look at, let's just pause this for a second. Let's select a really small time span. I'm just going to look at one of these little points when we did a throughput test. I don't think it's even able to to transmit very consistently just because of how crowded and how busy our environment is. So there's 10 seconds right there. And we can see that over that 10-second time span, we're utilizing the band about 50% of the time. So we're keeping it pretty busy. So what if we saw something like this? What if we saw that we had high utilization on a channel and we want to get a closer look at that conversation? That's when we use packet analysis. That's when we want to capture all of those wireless frames that are happening on that channel. That's when we want to look and see exactly what's going on with MetaGeek Lab to really get a closer look at what's going on. So if you see non-Wi-Fi interference, we need to find it and remove it. If you see Wi-Fi activity, that's when it's time to break out the packet analyzer to see exactly what is going on. So let's think about how these two things relate to each other. Spectrum analysis shows us the sum of all of the radio activity on the channel. It basically shows us all of the raw radio frequency activity that's happening on that channel. Remember, that includes everything that's talking. Not only is our throughput test, but it's all my neighboring networks and all the non-Wi-Fi devices and all the background noise. That shows us everything. Packet analysis, instead of looking at layer 1, that's the raw radio frequency activity, we're moving up to layer 2, the frame layer, and we're showing the details about 802.11 congestion on that channel. We're basically looking at all those little packets as they fly through the air, and we're getting a much closer look at what's going on. So when we're thinking about this, we've got to stop and think about all of the different types of wireless frames that you might see out there. We've got to stop and think about, okay, how exactly does Wi-Fi work? How does 802.11, that's the name of the protocol, how exactly does 802.11 work? And to really understand that, let's start digging into some of these different types of frames that you'll see in Wi-Fi. There's three different main types of frames that you'll see. You'll see management frames, control frames, and data frames. And we're going to demo IPA coming up here pretty quick. There's actually a really awesome cheat sheet for all these different types of frames. So here's a frame, or here's a frame type, a management frame, and then here's the subframe types like beacons and probe requests. If you don't remember what all this is off the top of your head, there's a cheat sheet built into IPA that I'll show you a little bit later on. So let's dive in and let's take a look at management frames first. What do management frames do first? Well, I hate to be the guy that reads off the slides, but man, I can't put it any better than this. Management frames manage stations joining and leaving wireless networks. So they help stations join and leave wireless network. The most common type of management frame is a beacon. A beacon is just a continual announcement of an access point's existence. So let's say that I'm on my Mac right now. Let's say that you open up the Wi-Fi menu to see which networks are nearby. We know about those networks because of beacons. Every access point sits there and continually beacons to let network or other devices nearby know that it's there. So for example, at home, my access point at home will sit there and go, hey, I'm Joel's network. I'm here. I support these data rates. I support this type of encryption. Hey, I'm Joel's network. I'm here. I support these types of data rates. I support this type of encryption. And it just continually announces that it's there by transmitting those beacons. And so when you open up the networks menu on your iPhone and you see the list of networks, we know all of those are there because of beacons. The next type of subframe is a probe. A probe is kind of the opposite of a beacon in that when you connect to a network, your phone or your laptop or your tablet or whatever, it remembers that network. And so let's say that I'm at home and I leave the home and I head to work. And I'm in the elevator at work, and the whole time that I'm driving to work, my phone is sitting there going through the list of networks that it's connected to in the past. It's going, hey, MetaGeek, are you there? Hey, Joel's network, are you there? And it's just going to continually do that. It's going to continually probe for familiar networks. And once I'm going up the elevator at work and it goes, hey, MetaGeek, are you there? MetaGeek will reply and say, yes, I'm MetaGeek, I'm here. And then we start that process of getting authenticated to the network and then getting associated, getting tied into our network. So beacons, probes, authentication, and association frames are all management frames, and they all help stations join and leave wireless network. Now the next type of frame is a control frame. What do control frames do? Well, they control the RF, that's the radio frequency medium, and they aid in the delivery of other frames. So the first type of control frame, the most common, is an ACK. Now, do you remember when we talked about the half-duplex nature of Wi-Fi? You remember that at the beginning of the webinar, and we also talked about it in the spectrum analysis webinar, how we send data and then we reply with an ACK or an acknowledgement. That's exactly what this is. An ACK is just a reply to say, yep, I received this frame. So we send data and then we send back an ACK to say, yep, I received this frame. Now, that takes a long time, right? Going data, ACK, data, ACK, data, ACK, data, ACK, right? You have to spend a lot of time saying ACK. And so block acknowledgements were one improvement that was made mandatory with 802.11n. Now, block acknowledgements basically acknowledge a block of data frames all at the same time. So instead of going data acknowledgement, data acknowledgement, data acknowledgement, data acknowledgement, we can go data, 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 acknowledgement, data, 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 acknowledgement, right? It starts sounding a lot like a System of a Down song. So with block acknowledgements, we can acknowledge a block of data frames all at the same time. Now, there's a couple more that are part of control frames that are kind of fun. RTS and CTS, and these ones are very, very closely tied together. RTS stands for request to send, and CTS stands for clear to send. And so we can use this to request some time to send and to send a reply saying, yes, you are ready to go. You are clear to send. And so let's talk about for a moment exactly what this means and what this looks like. And to do this, I'm going to draw some stick figures, all right? So get ready for some amazing mouse and keyboard art here. So at the MetaGeek office, our old office, we moved into a new office about a year ago, but back in our old office, we had a floor plan kind of like this. We had a kitchen right here, and there was like a sink right here and a fridge right here. And at MetaGeek, they keep the fridge, they kind of keep it stocked full of snacks and stuff in case you forget your lunch and things like that. There's some fruit and things there, which is pretty nice. And our IT guy, his name is Rich, he was sitting out here at his desk. So there's Rich sitting behind his desk. And standing here in the doorway was our reseller manager, Lael. And I'm sorry, rather, Lael was over here by the fridge, and I was standing in the door. Now, Rich and Lael, they couldn't see each other, right, because there was a wall between them, but they could both see me. And so all of a sudden, at the exact same time, they both asked me a question. They both started asking me a question at the exact same time. And I had to go, whoa, 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 hey, Rich, hey, Lael, you guys got to, you're both talking at the same time. I can't understand you at the same time. This happens in Wi-Fi as well. If I was an access point and Rich and Lael were both Wi-Fi devices, if they can't see each other, if they can't hear each other, there's a possibility that they might both start talking at the same time. And that's where request to send and clear to send comes in. So maybe if Lael had said, if she had said, hey, Joel, can I ask you a question? And then I would have replied saying, yes, you can ask me a question. That's like sending a clear to send, and that alerts Rich that he needs to be quiet for a moment so that Lael and I can have a conversation. That's exactly what RTS and CTS do. A device will say, hey, can I send right now? And then the access point might reply, yes, you are clear to send, and that lets everything else on the channel know, hey, we're having a conversation right now, be quiet for just a few seconds. So that's what RTS and CTS do. A stick figure art's pretty good, huh? So the last type of frame is a data frame. Now, this one's kind of obvious. Data frames carry higher level protocol data. This is the whole reason why we have wireless networks at all, is for data frames. These are the frames that actually carry the data, and these are also the only frames that make it onto the Ethernet side of the network. The management frames and the control frames, they get dropped at the access point. We don't care about those. The data frames, the contents of the data frames, which is packets, are the only thing that gets carried through to the Ethernet side of the network and out to different parts of the network or out on the internet or what have you. So there's three different types of data frames. First off, there's a data frame. That's just a standard old frame. And then there's a quality of service data frame. This is a data frame that's got some quality of service data attached to it. And this allows us to prioritize certain data frames over other data frames. So for example, let's say that we've got a couple of users on the same wireless access point. One of them is browsing Facebook, and one of them is doing a FaceTime call. Now, which one of those things is more important to get the packets delivered reliably and more quickly on? The FaceTime call. We've all been on a voice over IP call where the connection got kind of hazy or something like that, and the person on the other end starts sounding like a robot, right? That's what happens when we stop delivering packets in a consistent and timely manner. What quality of service data frames allow us to do is they allow us to put a priority tag on those frames. And so we can say, if we're looking at a few different frames that need to be transmitted across the air, the access point can look at this frame and go, you know what, that's just a background frame. That frame is just Facebook. We don't care about that. It's okay if it takes a second longer. However, this frame is a big deal. This is like this is a data frame, or this is a voice data frame. We need to get that one transmitted first. And so quality of service data frames allow us to prioritize those. And then the last type of data frame isn't really a data frame at all. It's a null data frame. These are used for things like power save polls and things like that. They don't actually carry data, so they're not really a data frame, but there just wasn't anywhere else to put them, and so they ended up being classified as a data frame. So watch out for that. You will see those. So how do devices, with all these different frame types, let's bring this all together. Let's talk about how devices decide who gets to talk next. Now, this is kind of crazy, all right? So, I don't know, maybe hit pause on the other YouTube video you've got playing or something like that and pay close attention to this because it's kind of hard to keep track of, okay? I'll try to keep it as simple as possible. Now, over here on the left-hand side, we've got a bunch of different stations, right? A station is either a client device or an access point. It doesn't matter. It's just a Wi-Fi device of some type. So we've got station 1, station 2, 3, 4, 5, and 6. We've got 6 different stations, and we've got time moving from left to right, okay? So now we're going to take a look at how devices decide who gets to talk next. How is it that all these devices share the same channel and take turns talking so efficiently? So we're going to start down here with station 6. At this point in time, station 6 is just finishing up sending some data, and then there's a SIFS, that's a short interframe spacing. It's kind of like a breath between words like I just took. It's just a little bit of a breath between those different frames, and then station 5 transmits its acknowledgement. So we have our data frame, and then we reply with the acknowledgement. Now, both station 2 and station 4, they both have something that they need to transmit. They both have something that they need to say. So they're going to basically roll the dice and decide who is going to talk next. So they're both going to roll the dice, and station 2 rolled 7 back-off slots, and station 4 rolled 9 back-off slots. Now what they're going to do is they're going to count up through those back-off slots in unison. And then as soon as the lowest number runs out of back-off slots, it'll start talking, okay? So they're going to count up together. They're going to count in unison quietly just to themselves. 1, 2, 3, 4, 5, 6, 7, and then station 4 is going to go 7. And, because station 9 just started talking. Station 9, station 2 rather, counted all of its back-off slots. It counted up to 7 and went, yay, nothing has talked yet. I counted all the way to 7 and nothing started talking, so it's my turn to talk. So you see how they did that. They rolled the dice, they counted in unison, and the one with the lowest number started talking first. So now station 2 is using RTS CTS with its access point, or with its client device rather. So it's going to send its request to send, and the other station is going to reply with a clear to send. It's going to say, yep, you're clear to send. So here's what happened. When station 2 transmitted its request to send, that let station 4 know, okay, something else is talking. I need to back off. But when it backs off, it's going to keep its back off counter. 9 minus 7 is 2, so now its back off counter is 2. And then when station 1 transmitted the clear to send, it's also going to let everything else know on the channel, okay guys, everybody shut up because we are talking for this duration of time. They're going to all set a nav timer. It's called a network allocation vector. They're all going to set a nav timer, and they're basically going to all synchronize their watches and go, okay guys, everyone shut up for this amount of time. These guys are having a conversation. That's what a nav timer is. So now station 2 is going to send that data frame, and station 1 is going to reply with an ACK, and we're done. We have now had a nice little conversation between station 1 and station 2. And now station 2 has some more data to transmit. So it's going to roll the dice again because it wants to get in there and transmit again. And station 4 didn't get to transmit the first time around either. So now it's going to get in there as well. But instead of rolling the dice, remember, it already backed off, right? And so it kept its back off counter of 2. So now its remaining back off is only 2 slots. Whereas station 2 is starting over, so it's got a back off of 10 slots remaining. So now they're going to count up in unison. 1, 2, and station 4 is going to go 3. Okay, it's my turn to talk. And so it's going to transmit its data. And when it does, station 2 sees that and sets a nav timer and defers and backs off. So station 4 transmits the data, and then station 3 replies with the acknowledgement. So let's just let that sink in for a second. This is happening millions of times a second. Do you have a cell phone in your pocket right now? Is Wi-Fi turned on? This is happening millions of times a second in your pocket right now on your cell phone. Every device on the same channel is constantly doing this, and it's happening super fast, unimaginably fast. So next time the Wi-Fi doesn't work, next time that Wi-Fi gives you some trouble, you might sit back and think, wow, it's kind of amazing that this works at all. It's kind of incredible that this works at all. It's so crazy how quickly this happens. So how do we deal with this? Well, we're going to deal with it with a packet analysis tool. Now, kind of the classic packet analysis tool out there is Wireshark. And Wireshark is great. We absolutely love Wireshark. We think it's one of the best things out there. It's absolutely fantastic, right? So Wireshark, the problem with Wireshark, even though it's a great, excellent tool, is that it displays packets in just kind of this linear fashion like this. There's a packet, there's a packet, there's a packet, there's a packet. It doesn't really help us visualize airtime usage. It doesn't tell us who's talking slow, who's talking fast, who's repeating themselves, who's eating up all the time on the channel, who's not eating up time on the channel. It doesn't really tell us that. And so that's why we need a dedicated packet analysis tool. So we came up with a tool called IPA. IPA stands for I Packet Analysis. It's a visual packet analysis tool. And we also really like beer at MetaGeek, especially good craft beers. So yes, we totally named one of our products after beer. IPA also uses these multi-layered pie charts, and they kind of look like eyes, and so there's several reasons why we call it IPA. And what these charts do is they show information in layers. So the total pie chart shows us the total amount of time that was used on the channel during the packet capture, how much time was used on that whole channel during that entire packet capture. And so then we can look and see what constituted all that time, right? So the innermost layer is our network. In this case, it's a network called Bronco Guest. That's the name of the network. And we can see that Bronco Guest took up about 2/3 of the total amount of airtime on this channel. So 2/3 of the total amount of airtime was taken up by Bronco Guest. And then the next layer in, this is the individual access point that's part of that network. So remember, a single network can have multiple access points. So this particular access point took up about half of the total airtime. There's another access point right here that took up, I don't know, what's that, 1/8 of the time on the channel, but this particular access point took up about half of the total amount of airtime. Now, there, of course, are clients connected to that access point, and we can see how much airtime those devices took up too. In this case, we could see this client took up about 1/3 of the amount of airtime, somewhere between 1/3 and a half of or 1/4 of the amount of airtime. And then if we go one more layer out to the outside, that outside layer shows us our frame type by color. So let's take a closer look at that. Remember how I had different colors assigned to the different frames? We had our control frames, that's our acknowledgements, our block acknowledgements, our RTS, CTS. Those are all colored in orange. And then our management frames, that's our beacons and our probe requests and probe responses, those are all colored in purple. So we can see where all those purple ones are as well. And then our data frames, that's our real-world data, is colored in blue. So you can really quickly look at this and see how much of this is management overhead and how much of it is actual data. And so now you start to understand why, just because our MacBook says it's getting 300 megabits per second, why we're not able to actually get that data rate, because there's a lot of management overhead that goes into this. A lot of these frames, a lot of these wireless frames are just part of managing the wireless network, and that introduces some overhead that we have to think about. So what I'm going to do now is I'm going to jump into a demo of IPA. Before we jump into the demo, I'm going to show you a couple different ways that you can get PCAP files. But here's just some kind of top things that IPA is really great for. It's really great for identifying top talkers. It's great at identifying devices that are having slow and inefficient conversations. And it's great for seeing which devices are transmitting the most data. It's great for identifying problem devices. You can pinpoint slow conversations that consume airtime, and it will also automatically point out devices that repeat themselves all the time. Remember those retransmissions when you have to retransmit something. It also will show you expert tips. It will automatically show you clients that have excessive retry rates, and it will identify network settings that could hurt performance. And one of my favorite things is that you can export all the data to Wireshark. So you can turn IPA into a really powerful filtering tool. So IPA and Wireshark get along dates. They hold hands and they get along great. They hold hands and go on dates and stuff all the time. So how do we get packets into IPA? This is one of the more challenging things about packet capture. The way that we do it the most at MetaGeek is with an AirPCAP NX. Now, SnapAV does not sell this product. MetaGeek does, and you can buy it directly from Riverbed. However, while this device is directly supported in within IPA, there are some downsides. First off, it is 2.4 and 5 gigahertz, which is nice, but it does not support 802.11ac, so keep that in mind. So there's some drawbacks, there's some advantages. The advantage is it's easy to use if you're stuck in a Windows environment. It's a great way to get PCAP files in Windows, but remember that you're not going to get 802.11ac frames. It can't understand those frames, but you can capture directly into IPA. Probably my favorite way to get packet captures is actually with OS X. With a Mac, you can get packet captures natively. Most Macs are both 2.4 and 5 gigahertz, anything that's relatively new at all. a MacBook Air like I have has a 2x2, so it has two spatial streams, and a MacBook Pro has 3 spatial streams, probably making the MacBook Pro one of the best capture devices on the market. And you get 802.11ac on late 2013 and newer models. Unfortunately, mine's a 2012, and so I do not have 802.11ac support on my Mac. And of course, there are some other sources. You can get them from Linux if you're pretty good with the command line in Linux, just with a normal off-the-shelf Wi-Fi adapter, and you can get them from some enterprise-grade access points. So there are some various ways that you can get PCAP files. Now you might be wondering, why do we have to use the Air PCAP NX when we're in Windows? Well, Windows has a pretty big limitation in that if we try to do packet capture in Windows, Windows throws away all the management frames and all the control frames, and it throws away all the data frames that aren't destined for your machine. And so ultimately it looks like Ethernet traffic by the time it gets to us, which unfortunately is not useful for wireless packet analysis. So my favorite way is by using OS 10. So let me show you how to do that really quick. So doing a packet capture in OS 10 is pretty easy. So what you'll do is on your Mac you'll hit Command space and you'll type in wireless diagnostics and hit enter, and it's going to and then you're going to hit Window and click Sniffer. You can also just press Command 6. And that's going to open up the network sniffer. Oh, it opened up on my other display. That's why. And then you can simply choose the channel that you want to capture on and choose your channel width and start your capture. Now it's going to ask you for your administrator password. It puts your Wi-Fi adapter in monitor mode. So now my Wi-Fi adapter on my Mac is listening for wireless networks. You can see there it's in monitor mode. And so then when we click stop, it's going to pop a WCAP file onto your desktop. It put it on my other desktop on my Thunderbolt display, since it's my primary display and not this one. So there's that WCAP file that we just generated. And so now you can either move that over to your Windows machine, or if you're like me and you just run it in a virtual machine, you can just go over to your virtual machine and fire up IPA and then open up that PCAP file. So if we just open up IPA here, I'm going to close Channelizer since we don't need that to be running anymore. And so we'll go over to File and hit Open File, and now we can open up, that's the packet capture. I just have desktop sharing enabled between my Mac and my virtual machine. Okay, so let's show you what this looks like, though, with the Air PCAP. So I've connected an Air PCAP, and I'm going to start capturing all of the packets on the channel right now. So you can see the file size here. You can see how many packets we've got. We've already got 3,000, now 4,000 packets. And you're going to see some invalid packets. That's okay. We're not going to understand every single packet that we hear. So now what I'm going to do is let's go ahead and kick off a throughput test with iPerf to generate some traffic with that. So I'm going to come back over here. We'll just hit up on the keyboard and hit Enter to run that same command again. So now we're doing our throughput test over Wi-Fi from my USB Wi-Fi adapter to my WRT54G, and then over to my little Raspberry Pi. Let's do a couple times. How about a couple of them, just for good measure? And so then, if we look back over here, you can see that file size is, look at, now we're at 35,000 packets. And that just tells you how quickly we gather frames. So now that we're done with that, let's hit the stop button. And what IPA is going to do is it's going to look at how long each one of those packets took to send. It's going to calculate how much airtime all of those packets took. And so it'll finish parsing out that data in just a moment. And then we can start looking at that to see what happened. Okay, so in the airtime graph, remember this is representing all the airtime that was used over the course of this capture. We can see that MetaGeek Lab used up the most airtime. There are some other networks here, but none of them used a significant amount of airtime, like ACCO and MetaGeek Test 2 and MobiNet and AirNet. None of them used a significant amount of time on the air, but MetaGeek Lab did. It used a lot of time on the air. So we can see that there's only one access point that's part of it, and we can see that there's a client called Netgear. That's my Netgear Wi-Fi adapter, used up the most airtime. It spent most of its time sending quality of service data frames and a little bit of time sending acknowledgments. Now we can also see how much airtime was used over time by looking at the airtime over time graph above. So we can see it humming along right here at about 50% airtime usage, and then it spiked right here and stayed near I would say it's about 80%, 85% airtime usage. And then we had a little lull again here, and then it started up again. So we can see when we ran those two iPerf performance tests. So let's drill down into this. I'm going to actually click on the Netgear slice here to drill down into it to get a closer look at what happened. So notice up here in the airtime graph, we can see that all of the stuff that we have selected right now, the conversation that we have selected is colored in green, whereas the conversation that we haven't selected is colored in gray. And so, so we can see over here that we spent about 1% of the time talking at 1 megabit per second, but our most common data rate was 24 megabits per second. We used that about 30% of the time. So we really get an idea of how efficient that conversation was. Notice the retry rate. The retry rate was 31%, meaning this wasn't a very efficient conversation. We had to resend our frames a lot. It was kind of a slow and inefficient conversation. So now that we've drilled down into this device, we can go over here to the Packets tab, and that's going to show us all the packets that were part of that conversation. So we can see us sending the quality of service data frame, getting an ACK. We can see this constant process of data ACK, data ACK, data ACK, data ACK, data ACK. Now, one thing you may have noticed is that we're not using block acknowledgments here. Why is that? Why aren't we seeing any block acknowledgments? Well, that's because this is an 802.11g access point, and it doesn't support block acknowledgments yet. That didn't come until 802.11n. So the other thing you can see is our retries here. So remember our retry rate was 31%. You see this little circular flag, that basically says that that is a retry. We had to resend that data frame, which is amazing considering that we're only 6 feet away from the access point. We really should be seeing better than that. And so let's say that we wanted to get some expert tips as to what's going on this wireless network. If we go to the Analyze tab, we can find our network here. So here's MetaGeek Lab, and put a checkbox next to it, and it's going to tell us some interesting things that it noticed about that wireless network. First off, it's noticed that we have legacy data rates detected. It found some data rates of 1 and 2 and 5.5 and 11 megabits per second enabled. Allowing devices to talk slowly with those slower, older data rates consumes more airtime. So you can click Learn More to learn some more about that, or you can hit Too Long, Didn't Read to collapse that back again. We also noticed that an 802.11b protection mechanism is enabled, which will slow things down as well. And we noticed that this specific device, this Netgear device with this MAC address, had a 30% retry rate. And we call out some reasons as to why that might be. We say, hey, you might have some Wi-Fi chipset issues. You might have overlapping channel interference. I can guarantee that's the problem. And we can, and maybe we need to remove some non-Wi-Fi interference that's causing problems. So IPA will try to intelligently suggest what might be wrong with your wireless network. And so you can really quickly get in there and look at those conversations to see whether it's a specific client device that's performing poorly, that's essentially bringing the whole channel down. Okay, so I'm going to go open up a sample capture. If you get IPA on trial and you don't have a Mac and you don't have an AirPCAP or a good way to get PCAP files, if you get a trial version of IPA, you can open up this this sample capture file. It's called iPads.pcap. And basically there was an enterprise-grade vendor who was streaming video to 100 iPads at the same time on an expo floor, which we thought was pretty amazing. Have you ever tried to use the Wi-Fi at a convention or at an expo or something like that? Usually it sucks, because there's so much stuff using the air. So of course we had to get a packet capture of this to see how they were doing it. So so when we open up this packet capture, we could see that really this network called iPad Demo 6 was really the only network that talked on this channel. We can see that there was another network called Voice WLAN 2 that didn't talk very often, and another one called HP Blogger M, but they really didn't spend that much time talking. iPad Demo 6 had only one access point, and it had multiple client devices connected to that access point, and they all used about the same amount of airtime. And of course these are all Apple devices, and so I'm going to assume that's probably the iPads. So we can click on those to open them up and to see exactly what happened during that packet capture. Now we can see that it was mostly quality of service data frames, the little bit of block acknowledgments. What's going on there? So let's go to the Packets tab and take a look. We can see that one way that they conserved airtime was by using block acknowledgments. So instead of going data acknowledgement, data acknowledgement, data acknowledgement, they went data, 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 acknowledgement, request to send, clear to send, data, 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 acknowledgement, right? And so they were able to conserve airtime by using those. They also used some nice fast data rates. The slowest data rate they used was 6 megabits per second, but they were often able to hit 58 megabits per second about 25% of the time. And if you look at the top here, Another way that they were able to stream video to 100 iPads concurrently was by having them buffer their video at different times. So if we look at the first device, you can see at what point in time it buffered its video here. And if we back out and look at a different device, we can see that it buffered its video at a different time. And then this device buffered its video at a completely different time, a little bit right here and then a little bit later on. So you can see when devices were buffering their video, and that's part of how they were able to stream video to 100 iPads all at the same time, all on an expo floor. Okay, so the last thing I want to show you really quick is the integration with Wireshark. Let's say that you have an Apple device here and you want to take that entire conversation and you want to send it to Wireshark. So to filter down to it, let's click on it. We've now drilled down into this. And then let's say that we go over to the Packets tab and we decide that we only want the data and the block acknowledgements. We don't want the RTS CTS. If you click on the subframe filter bar up here, we can go in here and we can uncheck RTS and we can uncheck CTS, and that's going to remove those two types of frames, leaving us only with the data frames and the block acknowledgements. You see how easy that was? 2 clicks and I just filtered out 2 different frame types. You can also filter by SSID or access point vendor, by client vendor, by MAC address, even by data rate and signal strength received. All these filters are super easy to use. And so let's drill back down into our Apple device. So now we've got the RTS filter applied, the CTS filter applied, and we've drilled down into this device. And so then let's click File and click Send to Wireshark. That's going to wrap up all these frames, going to put a bow on them, and send them over to Wireshark for deeper packet analysis. So if you want to really get deeper into these wireless frames to really get a closer look at what's going on, you can get them over into the tried and true good old Wireshark to really take a closer look at what's going on. Okay, I think I'd like to hand it back over to either Heidi or Ahem now.
All right, Joel, thanks a lot for the information. I hope it makes sense for all the folks here on the call. I will make myself a presenter for 1 second. Hope you guys see what I have. So I just want to remind everyone here on the call all the different packages that we partner with MetaGeek on. The basic package will include the WiSpy DBX, the Insider Office. The professional package will get WiSpy DBX and Channelizer. And the advanced package, which we cover today, includes WiSpy DBX, Channelizer, and IPA. We do also sell heat mapping software, Thermograph Pro, a la carte, that you can buy it with any other packages. And just a reminder that if you buy it from any of the stores, SnapAV or IL8, you get 10% off of MSRP. Also a quick reminder before we go to Q&A about our lineup of access points for Arachnus. We have the 100, 300, 500, and 700 series access points. They're all indoor, range from single band N in 100 series, dual band concurrent N in 300, dual band concurrent AC 2x2, and dual band concurrent AC 3x3 in 700 series. They're all standard PoE powered. They're all high power output. Yeah, they're all support oversea cloud management, and they all support fast roaming natively. And with that being said, we'll open the floor to some Q&A with Heidi and Joel.
All right, thanks guys. Looks like we have about 5 minutes left for Q&A. As a reminder, you can send in your questions using the question and answer feature in the webinar control panel. All right, Joel, first question. When you disable the SSID broadcast, does that access point still send out beacons?
Yes, it does. So one common misconception is that disabling the SSID broadcast or cloaking your SSID is a security advantage. It is not. Here's why. The beacons are still broadcast, they just don't have the name of the SSID included. So all the information is there except for the name of the SSID. Now most operating systems won't show that SSID in the list. When you connect to that SSID, you have to give your SSID, and then your devices have to probe for that SSID. So let's say that Joel's network was hidden. My device has to probe for Joel's network to discover that network and connect to it. So we have to probe all the time. So most people believe that disabling the SSID is a kind of a security thing. It can help make your network more secure. Unfortunately, it cannot. It is extremely easy to discover a hidden wireless network. The one use case for that is if you're just tired of people asking if they can connect to your Wi-Fi. That's probably one use case for cloaking your SSID.
All right, thanks. Next question. When you delete or filter a cordless phone in Channelizer, how does that work if it doesn't modify what the phone is doing?
Well, the idea is that you identify the cordless phone in Channelizer, and then you go physically remove it. Now you can't filter it out, you can't jam it. There's nothing you can do other than identify it with Channelizer and go find it and go remove it.
Okay. When you have a device with a constant transmission on a channel, for example, an AirPlay device, how is that handled with other devices on that channel?
Well, you remember how we talked about the Airtime arbitration process, how wireless devices kind of decide who's going to get a chance to talk next. They basically all just kind of go to battle and they roll the dice and they decide which device is going to talk next. The trick is that eventually you're going to get to a point where that AirPlay device isn't going to have enough time to be able to get on the channel and say what it's going to need to say, and that's when you start having video dropout issues and things like that. So if you're having trouble with an AirPlay device not working well, that's when you need to do a PCAP and see what is going on that channel to see why that device is having trouble, because you can look at that conversation up close.
All right, thanks. For those who aren't familiar with the concept of fast roaming, can you give a quick overview of how that works?
Ooh, that's a tough one. Probably a bit outside the scope of that webinar. I'd love to get into that right now, but I don't think we have time. Basically, with fast roaming, APs are able to buffer packets on the next access point that the device is going to roam to. And then when the device roams to that access point, the AP will give that device all the frames that it buffered. So I wish we could get into that, but it's a bit outside the scope of this webinar, unfortunately.
Okay.
Yes, and I would add that if you look at our history of webinars, we did a webinar about fast roaming when we introduced it that explained it very well. So you guys can look at that into either SnapAV or File8 inventory or vault of resources, or you can find it on YouTube somewhere.
All right, thanks guys. Next question, what is the most common higher level parameter that can have a positive effect on a congested Wi-Fi network?
The highest level parameter, I would say one of the best things that you can do to improve congestion problems on your wireless network is disable legacy data rates. Disable data rates like 1 or 2 or 5.5 or 11 megabits per second. You're basically going to force all of your devices on your network to talk faster, so they can't slip down to those lower data rates. Now, one thing that does do is it does shrink your coverage area slightly, because when you move away from that access point, you can't quite go as far away because we can't fall back on those legacy data rates. In very high density networks like stadium deployments, it's very, very common for engineers to disable lower data rates. I've even seen networks where they disabled everything below 24 megabits per second. So that's probably a bit extreme for most environments, but in some of those environments, that is what you have to do, is disable those legacy data rates.
All right, thanks Joel. And last question, can you just quickly recap the options for using IPA on a Windows PC or laptop?
Absolutely. So let's see if I can take the screen back. I'm not sure if I can. So the three different options the options that are out there for wireless packet capture in Windows, really the only good PCAP option, thank you very much, is the only really good option out there right now is the AirPCAP NX. It's the only really good way to capture in Windows. The other alternatives are to use OS 10, not iOS. This is not going to work on an iPad or an iPhone. They don't have that functionality, but on OS 10 you can do packet captures, or you can get them from Linux or from an enterprise-grade AP if you're pretty good with that sort of thing. So really the AirPCAP NX is really the only current way for us to get PCAP files in Windows.
All right, thanks Joel. Looks like that's all we have time for today. I want to thank everyone for joining us and remind you to be on the lookout for a follow-up email within the next few days. We'll have a link to a recording of today's session, as well as a coupon code for $50 off the MetaGeek Basic, Pro, or Advanced packages. And lastly, as you're exiting today, we would ask you to take a few quick minutes to complete our 3-question survey to let us know what you thought about today's webinar and what you'd like to see webinars on in the future. And with that, we hope you have a great day and see you next time.